In this video, we're going to take a look at the last two trends, which is metallic and non-metallic character along with reactivity. So we'll start off with metallic reactivity and metallic character, and then we'll go on to non-metal reactivity and non-metal character. So what exactly does that all mean? Well, let's talk about metal reactivity first. Metal reactivity is just how reactive a metal is, or how likely it is to react by giving away its electrons, by losing its electrons. Because remember, that's typically how metals act when they react. They will donate, or not donate, but they'll lose their valence electrons. So if you're more likely to do that, you have a higher metal reactivity. So associated with that idea is metallic character. So basically, how good of a metal are you? The metallic character is basically just properties associated with metals. So that's things like you're soft, you're malleable, you're ductile, you're lustrous, you're conductive. That's all part of metallic character. Now, generally, as I mentioned before, metals tend to lose electrons, and they conduct electricity very well because they have a weaker hold on their valence electrons. And electricity is all about movement of electrons. So if you have a weaker hold of your electrons, then you're more likely to be able to conduct electricity. That explains that conductivity piece of the metallic character. So we notice some trends in our periodic table. The metallic reactivity usually decreases from left to right. So for example, lithium is a more reactive metal than beryllium, or sodium is a more reactive metal than magnesium, and magnesium is more reactive than aluminum. So in other words, you're more metallic towards the left side. If you were to think of all the elements as sort of one type, as you go towards the left, you're more metallic, and you're less metallic on the right side because you're basically non-metal. So you're non-metal on the right, and then you become more and more metallic as you go towards the left until you're really kind of all metal. So left side has the most metallic characters there. And the other trend is from top to bottom, you become more metallic as well. So lithium, sodium, potassium, the reactivity will actually increase in terms of metallic reactivity as you go from top to bottom. So for example, francium is more reactive in terms of its metallic character and metallic reactivity compared to lithium. And so why do those trends exist? Well, for the left to right trend becoming more metallic towards the left side, that's because you're less metallic on the right side because you have a greater effective nuclear charge. So, for example, fluorine is a greater effective nuclear charge, and as a result, it's going to hold on to its valence electrons, and it's not likely to lose electrons. And to be metallic in terms of metallic reactivity or character, you need to have a weak hold of your electrons. So, too far to the right, and your hold on electrons is too strong to be metallic. But if you're more on the left side, your effective nuclear charge is smaller, and you can give up the electrons more easily and therefore act like a metal, which is giving away electrons and being conductive as a result of that as well. Towards the bottom, why you were more metallic? Well, that has to do with more energy levels. There's more shielding, and because there's more shielding from the nucleus, the outer electrons can be donated more easily compared to something that's higher up. So lithium can give away its electron easily, but not as easily as, let's say, potassium, which has more shielding, and that's why it can give away its electron more effectively. So those trends, once again, are explained by effective nuclear charge and shielding. Here you can see various examples of different metals, various examples of metals from the periodic table, and you can see some of the characters that we discussed. So, for example, you might see that some of them are quite lustrous. So you can see that in the image there. You can't really see conductivity, but you could test conductivity, and you would see that they would conduct electricity. And then our most metallic element is francium, because it's all the way to the left and the bottom. But there is some debate on that. And like I said, you could research that because there's often debate as to is it cesium or francium that's considered the most metallic. And again, you can read up on the debate. But for now, we're just going to go with francium just because it's based on that periodic trend. And then the same idea of non-metallic character exists as well. It's typically for non-metallic character and reactivity, it's rather than the ability to give away electrons, it's the ability to react by gaining electrons, because non-metals usually gain those electrons. And so the trend is sort of the opposite of what you would see for the metallic character. Non-metallic character increases towards the right side, whereas metallic character, the increasing is towards the left side. And also non-metallic character increases towards the top because again, similar ideas. Towards the right side, you have a stronger effective nuclear charge, and you're more likely to attract electrons, which is what non-metals do. And then towards the top, again, you have less shielding, and because you have less shielding, you're more likely to attract electrons, and that's again something that non-metals are supposed to be good at doing. So the most non-metallic element, the one that's really good at gaining electrons, is the one that's also most electronegative as well, is fluorine, because it has a really good ability to attract electrons. Um, so you can see here just a comparison of metallic versus non-metallic. So you have our metals over here, lustrous, for example, and this is all the way on the left side of the periodic table. So it's very metallic; it can give away its electrons quite effectively. And then here you have sulfur, not very lustrous, a yellow solid powder at room temperature. And it's not a good conductor because it has a stronger hold of its electrons compared to, let's say, sodium, and it's likely to attract electrons rather than give away its electron just because it has that greater effective nuclear charge as well. So what we're going to do is we're going to fill in some blanks, and then afterwards just rank elements based on metallic character, non-metallic character, and take a look at some relationships that exist between metallic character, non-metallic character, and all the other trends as well. And then there's some additional practice problems that you can try over here for metallic character, and you can see answers to these problems here and here with some additional practice problems in there. But as usual, the main homework problems are found in the learning goal area. So let's go ahead and fill in some blanks, and then try some problems together. So remember, metallic reactivity refers to the degree to which metals tend to react by losing or giving away electrons. And the metallic character refers to properties that are associated with metals, like being soft, malleable, ductile, lustrous, and conductive. And the reason that metals tend to lose electrons and the reason they're able to conduct electricity is just because they have a weaker hold on their electrons, right? It has to do with their position in the periodic table, with their effective nuclear charge, and their shielding. They're more towards the left side of the periodic table, so they have a lower effective nuclear charge compared to other elements just because they have fewer protons compared to elements more to the right of the periodic table in their period. So trend one, metallic character from left to right. So metallic character decreases from left to right. So for example, fluorine would be less metallic than, let's say, lithium, because lithium is more on the left side. And then fluorine's more on the right side. And the reason that fluorine is less metallic is because, well, it has a stronger hold of its electrons due to greater effective nuclear charge. And like I said, you're supposed to be able to lose your electrons as a metal. Or even a better example, let's compare two elements classified as metals. Lithium is more metallic than beryllium because it's on the left side, greater effective nuclear lesser of an effective nuclear charge, so it's able to give away its electrons more effectively compared to beryllium, even though beryllium can still do that. And then trend two is that when you go from top to bottom, the metallic character increases from top to bottom. And that's because there's more shielding, and it prevents the electrons from being held on too tightly, so you can give away your electrons more effectively towards the bottom. So essentially, I'll give you an example of that. Potassium would be more metallic than sodium. They're in the same group, but potassium is lower down, more shells, less attraction to the outer electrons, can give away that electron more effectively. And as we mentioned, francium would be the most metallic element. Like I said, there is some debate between cesium and francium, and you can research that, but we're going to stick with francium for now because it's all the way to the left and all the way to the bottom. And then we have our non-metallic character, which is the tendency to react with substances by, rather than losing, gaining electrons or accepting electrons. And that's what makes a good non-metal. And so it's essentially the opposite of the metallic character, metallic reactivity trends. So from left to right, the non-metallic character increases from left to right. So towards the right side, you're more metallic. You're more non-metallic. So for example, fluorine is more non-metallic than oxygen because it's more towards the right. It has a greater effective nuclear charge. It can grab onto electrons. And this doesn't really include the noble gases because we're defining non-metallic character as being able to gain electrons. So that's why it doesn't really apply to noble gases. And then the trend too, from top to bottom going down a group, the non-metallic character decreases. Because when you go down a group, there's more shielding and you don't attract electrons as easily. And you're not a very good non-metal if you can't attract electrons. So really, the most non-metallic element we're going to see is fluorine. Again, not counting the noble gases so much. So fluorine is the most non-metallic element that we can see. And again, that's because there's more energy levels result in weaker attraction due to shielding. There's many different words you can put here. I just want to make sure it's consistent with what we put for our slide deck. So let's go take a look. Due to shielding. That's right. Good. Perfect. And again, it's good to always practice like that. So go through the slide deck, watch the video, and then see if you can fill in the blanks yourself and explain things yourself. Let's go ahead and try these practice problems out here. So rank the following elements by, increasing metallic character. It should say increasing there. So that means from smallest to biggest. So let's take a look. Smallest, just by looking at this, just pretty straightforward. Oxygen is not even a metal. So I'm going to put oxygen as the smallest. Let's compare sodium and lithium. Let's compare cesium, sodium, and lithium because they're all within the same group. So we can do that. Cesium, sodium, and lithium. Cesium's all the way at the bottom here, and lithium's at the top. So metallic character, you want to lose electrons. More shielding at the bottom. So cesium is more metallic than sodium and lithium. Lithium would be the least metallic of these because it does have a stronger hold just because there's fewer shells. So lithium's the least metallic, then sodium, and then cesium is the most metallic. So it would be lithium, sodium, cesium. So lithium, sodium, cesium. We do need to compare beryllium to something. So I don't know where beryllium's going to fall. Let's go compare beryllium to, it's probably going to be more than oxygen. But is it more than lithium in terms of metallic, more than sodium, more than cesium? Let's take a look at beryllium and lithium. So, okay, beryllium is more towards the right side, and metallic character decreases as you go towards the right because you have a greater effector nuclear charge. So it's going to be less metallic than lithium. And it's going to be more metallic than oxygen, though, because it is a metal and oxygen's not, but it's towards the left of oxygen. So basically between lithium and oxygen. So that's from smallest to largest here, metallic character. And that's how you would go about to do that. So let's try these ones here. Consider the elements Li, Be, Mg, and A. And this is a good consolidation activity. It lets you see if you understand all the different trends. So which element is the most metallic? And based on this, let's take a look. Na, Mg, Be, and Li. So Be is out of the run because Mg is more metallic and so is Li. So it's not Be. So compared to Li, Na is more metallic. Compared to Mg, Na is more metallic still. So Na wins because it's more towards the left and more towards the bottom of all these elements here. So Na is the most metallic. Which element has the lowest electronegativity? Remember, electronegativity increases towards the right and the top. So beryllium has a higher one compared to all these four elements. Let's see, then lithium would be lower than beryllium. Sodium would be even lower, actually, because that's towards the bottom. And magnesium would be higher than sodium. So lowest would be sodium in this case here. Sodium is lower than lithium in terms of electronegativity, lower than magnesium in terms of electronegativity. So sodium has the lowest electronegativity there in that group. Which element of those four would have the largest atomic radius between all those? And it looks like, from the sounds of it, remember that atomic radius decreases towards the right. So I don't think the beryllium and magnesium will win because they're smaller than lithium and sodium because they're towards the right of them. So let's just compare between lithium and sodium. Towards the bottom is where you increase in radius. So sodium has the larger atomic radius. So sodium has the largest atomic radius. And then which element has the lowest ionization energy? Ionization energy increases towards the right. So it wouldn't be beryllium and magnesium. We'd be comparing between lithium and sodium. So it looks like ionization energy would decrease as you go down because there's more shielding. So sodium would have the lowest out of all those. So once again, sodium wins the game here, having the lowest ionization energy. And which one has the lowest affinity? Well, affinity follows the same trend. So that's again going to be sodium. And the reason I kind of showed you this is because you'll notice that all these trends relate to metallic character, right? So the point of metallic character is that you want to be able to give away electrons. So to give away electrons, you don't want a strong attraction to them in a bond. You want to be able to get rid of them. So you'd have low electronegativity. If you want to give away electrons, you should have a larger atomic radius because your electron will be farther away and you will hold on to it as strongly. You should have low ionization energy because you don't want to have to put too much energy in to get rid of your electron. You want it to be nice and easy. And you should also have low electron affinity. You don't want to really be accepting electrons, right? If an electron goes to you, you don't want to really give off too much energy and say, yeah, I want to do that. No, as a metal, you want to get rid of electrons instead. So you're not going to tip very well. So you'd have a low electron affinity. So typically metallic elements will have a lower electronegativity, a larger radius, a lower ionization energy, and a lower electron affinity. So the more metallic you are, the lower all those things are, except for radius. That's the larger it is. That's why francium is a very, very large atom. So its electrons really far away from it compared in the nucleus there. So that's why it will get rid of it very easily. And so that was some examples of metallic and non-metallic characteristics.